Okay, in this video, we're going to discuss more properties of DTFT. Let's look at basic properties of DTFT like linearity. So DTFT is a linear transformation. Basically, your x1 and x2 are two signals, and you are taking the Fourier transform. Then the Fourier transform will be the sum of or superposition of x1 Fourier transform with x2 Fourier transform, right? Uh, and how do you prove it? It's very simple. You know, x e to the power j omega is given by xn e to the minus j omega n summed over all n's. Now, you substitute xn with a1 xn x1n plus a2 x2n, and you see that everything will distribute evenly because the summation is that this product will be distributing over it, and you will simply get x1 basically a1 times x1 e to the power j omega plus a2 times x2 e to the power j omega. It's very simple. Okay, next, the next property, okay, if I reverse the time of my signal, basically if I flip my signal along the x-axis, let's say my signal was something like this, and I transform it into, let's say, this. So it means if it was some n naught here, now it is minus n naught here. Right? This is my x of n. This is my x dash of n, which is equal to x of minus n, and n is anyways in this direction in both the cases, right? So how do you prove it? How do you find the Fourier transform? Just go back to the basics. The Fourier transform is given by x of minus n multiplied by exponential of minus j omega n and summed over all the n's. And now you want to put it in a form which is x of e to the power j omega. For that, just substitute, replace n with minus n, right? Put n equal to minus m. What does that give us? So my x of m is basically, I obtain x of m here and here something different. To go back to my Fourier thing, I need a negative sign here. So I can write it like minus j omega or minus j of minus omega m. So this is equal to x of e to the power j of minus omega, which means x of e to the power minus j omega, right? So another property is time shifting. If I shift my signal in time, let's say I have some x of n is like this, and I transform it, I shift it in time. So which means, let us say I moved it. So when, let's say this was, the beginning of the peak was at 0, and now the beginning of the peak is at n naught. This is my n, this is my x dash of n, which is equal to x of n minus n naught. Then how will my Fourier transform change? So let us compute from the same formula, x of the new thing, e to the power minus j omega n, summed over all the n's. Now you want to go back to this representation, so replace n minus n naught with some m, and that gives you, okay, basically that will, so when you make the substitution here, you will get m plus n naught, and that whole thing will reflect like this, because the summation is over m, so n naught is a constant, so it can be taken out. So this proof is very simple, you can go through it. So basically what you're seeing is, it is introducing a phase term. So my x e to the power j omega is getting multiplied with a phase term. When I shift in the time domain, I get phase multiplication in the frequency domain. Okay, now let's see what happens if I shift my frequency. Basically, let's say my x e to the power j omega. Now I'm doing some operation in the frequency domain, and I want to see its effect in the time domain. This is my omega. I know it is periodic between minus pi to plus pi. So let us say my x omega was something like this. This means if I shift it, which means I want to shift it something like this. So this was at the center was at p0. I want to shift my center to omega naught. This is x dash e to the power j omega. So how does my original signal transform? In other words, if I in what way should I transform my time domain signal so that my Fourier transform shifts by an omega naught? It's very simple. Just compute the inverse Fourier transform of this shifted version. You can also go the other way around. You can compute the Fourier transform of this, or you can compute the inverse Fourier transform of this. Both are equivalent. Both will give you very easily. They'll prove the thing. They will give you the result. Now let's go this way. Now this same thing. You substitute omega minus omega naught with some theta, and corresponding phi term you will get here, and corresponding omega naught term will also be here, which will be taken out as common, and you will get xn. The very simple proof. Okay. Other way is that you start from xn e to the power j omega naught n and compute its Fourier transform. So this one will just merge into this part, and then you will get the right solution. Okay. Now another property is differentiation in frequency. If I want to differentiate my signal in the frequency domain, how will it look like? So this is a little bit involved. Let's go through it one by in steps. So let's go back to the basic definition. I want to compute the inverse Fourier transform of the differentiated version. I want to compute the inverse Fourier transform of this thing. So what I get is, so it is basically this thing. Now how do I integrate over this? If you remember the previous approach, you want to convert this into a standard form so that you can write it as xn. So how do I convert a differentiation into a standard form? So I have to integrate it, but integrate how? There are two terms involved. So the obvious solution which comes into mind is integration by parts. So what is integration by parts? If you have two terms multiplying each other, the integral over the product will be given by the first term, integral of the second term, minus the derivative of the first term and the integral of the second term and the integral over the whole thing. This is very standard integration by parts. So I have to select my u and v. So very simple. Let us take my u as e to the power j omega n and my v as the derivative term, because I am integrating over v here. So let us substitute the integration by parts formulation. So you keep your u as constant and integrate the v, and so because this is a there are limits involved, so I will take the limits from minus pi to pi, and then on the other hand I have the derivative of u now, and then the integral of the v, and now this one is in the standard form, right? You have x e to the power j omega, you have e to the power j omega n, and this one is very simple. The first part becomes 0, but the second part can be simply simplified, and it gives me n times xn. Very easy. Okay. Another thing is convolution. How do you do convolution in the time domain? If I'm convolving two signals x1 and x2, and how does the thing change in the frequency domain? In the frequency domain, it turns out that is simply the product of individual Fourier transforms. This proof is also very simple. Let us say I'm starting with this part. So my x dash of e to the power j omega is simply this thing times e to the power minus j omega n summed over all n. N goes from minus infinity to plus infinity. That is obvious, so I have just not written it. Now you just switch the integration, or the summation. Take the n terms inside, and only this term involves n. And you know what is the Fourier transform of this part. You have already computed that a time-shifted version, the Fourier transform is the original Fourier transform multiplied by a phase term, and that phase term is e to the power minus j omega k, right? I substitute it back here, so I get x2 e to the power j omega and then summed over k x1k times this term also involves a k, so this one also stays inside, but this whole thing is simply x1 e to the power j omega, right? So in this way I obtain that the new Fourier transform will be simply the product of x1 with x2 e to the power j omega. So this is about convolution. Let's see now what happens if I multiply in the time domain. It comes out, because the Fourier transform domain and the time domain, they are dual of each other, so they are kind of symmetric. So if I multiply in the time domain, I get correspondingly convolution in the frequency domain, and the convolution in the frequency domain can also be written like this. So notice that there is 1 upon 2 pi factor here. It is not simply the product and integration, but 1 upon 2 pi factor is also involved here. This is important. Okay, the proof is also very simple. Start from the inverse Fourier transform, start from the right hand side and take its inverse Fourier transform to obtain some x dash of n. And very easily you can prove using the same thing, just switch the limits, switch the integration, and so instead of integrating over d omega, instead of integrating over d theta, you integrate over d omega and take d theta out. So just a minute, there is, so this was x2 e to the power j omega theta. This term has an omega, and this term has an omega, and this is omega. So I take my d omega here. I take my d omega here and I obtain I take my d omega inside and my d theta is outside. Let us say I take my d omega inside, and this term is what you know is, okay, 2 pi times x2n into e to the power j theta. So a shift in frequency is like multiplication of the phase term in the time domain. Now likewise you consider the other term also now, e to the power j theta into x1 e to the power j theta. Some are integrated over d theta will give me x1 of n. So that's what I get. I prove the thing that this thing is equal to x1 of n into x2 of n. And the references for this part is again Oppenheim, chapter number 2, sections 7, 8 and 9. Thank you very much.